Try something for me. Stand up and try walking around your room on all fours for the next 10 seconds. Awkward, right? Slow. Uncomfortable. Your hands probably hate you already. Now here's the strange part. That awkward, uncomfortable position is exactly how almost every other primate on Earth gets around, every single day, without a second thought. Chimpanzees, gorillas, and most of our closest relatives move primarily on all fours, using their knuckles for support. It's efficient for them. It works. And yet, somewhere along the way, one branch of the primate family tree stood straight up, balanced its entire body weight on 2 feet, and never looked back. That's genuinely strange if you stop and think about it. Standing on 2 legs is harder to balance. It's slower in short bursts. It exposes your entire front side to a predator instead of protecting your organs low to the ground. On paper, it almost looks like a bad evolutionary decision. So why did we do it? Why did our ancestors give up a stable, efficient 4-legged stance for something that, at least at first glance, seems riskier and clumsier? Let's dig into it, because the real story involves treetops, energy bills, empty hands, and a set of footprints frozen in volcanic ash that still leave scientists a little amazed every time they look at them. First, let's clear up a common misconception, because it shapes this entire story. For a long time, one popular idea, often called the savanna hypothesis, suggested that our ancestors started walking upright because forests shrank and thinned into open grasslands, and standing tall helped them see over tall grass to spot predators and prey from a distance. It's a tidy story. It makes intuitive sense, and for decades, it was the dominant explanation. But here's the twist. More recent fossil evidence has seriously complicated that picture. Some of the earliest known hominins that show signs of upright walking appear to have lived in mixed environments, including wooded areas with significant tree cover, not open grassland. That doesn't mean the savanna hypothesis is completely wrong, but it does mean the full story is more complicated than grass got tall, so we stood up. So if it wasn't simply about seeing over grass, what else could explain such a dramatic shift? Let's start with the oldest evidence we actually have, because the timeline here stretches back further than most people realize. A fossil skull known as Sahelanthropus tchadensis, discovered in Chad and dated to roughly 7 million years ago, shows a particular clue in its anatomy. The opening at the base of the skull, called the foramen magnum, where the spinal cord connects to the brain, is positioned differently in upright walkers compared to animals that move on all fours. In creatures that walk on 4 legs, this opening tends to sit further back, since the head balances out in front of the spine like a shelf. In upright walkers, it shifts more toward the center underneath the skull, allowing the head to balance directly on top of a vertical spine, without needing constant muscular effort to hold it up. The position of this opening in Sahelanthropus suggests, though it remains debated among researchers, that some form of upright posture may have already been developing an astonishing 7 million years ago, incredibly early in the human evolutionary story. A few million years later, evidence from a species called Aurorin tchadensis, found in Kenya and dated to roughly 6 million years ago, includes a thigh bone with structural features that many researchers interpret as consistent with walking upright, at least some of the time. Then, around 4.4 million years ago, we get one of the most important fossil finds in this entire story, a remarkably complete skeleton nicknamed Ardi, belonging to a species called Ardipithecus ramidus. Here's where things get genuinely fascinating, because Ardi's skeleton tells a wonderfully messy, in-between story. Ardi's feet and hip structure show real adaptations for walking upright on the ground, but Ardi's hands and long curved fingers still look remarkably well suited for climbing and moving through trees. In other words, Ardi wasn't purely a ground walker or purely a tree dweller. Ardi appears to represent a genuine transitional stage, a creature comfortable moving upright on the ground, but still very much at home in the branches above. This discovery genuinely reshaped how researchers think about early human evolution. Before Ardi's skeleton was fully studied and described, many scientists assumed that our upright walking ancestors must have evolved from something resembling a modern chimpanzee, moving primarily through knuckle walking, before eventually standing upright. Ardi's anatomy challenged that assumption directly. The pelvis and lower body show clear upright walking adaptations, while the upper body and hands retain features suited for careful, deliberate movement through trees, rather than the specialized knuckle-walking anatomy seen in chimpanzees today. This suggests that upright walking may not have evolved out of knuckle walking at all, but instead emerged from an entirely different kind of tree-dwelling ancestor altogether, one whose descendants eventually split into separate paths. This tells us something important. Bipedalism probably didn't happen in one clean, sudden leap. It likely evolved gradually, with early hominins spending time both in trees and on the ground for a very long transitional period, slowly shifting their balance of time and anatomy toward life on 2 feet. Now, here's where the evidence becomes almost unbelievably direct, and it comes from a discovery that still gives paleoanthropologists chills. At a site called Laetoli in Tanzania, researchers uncovered a trail of footprints preserved in hardened volcanic ash, dated to roughly 3.6 million years ago. Not bones, not tools, actual footprints, left by walking individuals, almost certainly members of the species Australopithecus afarensis, the same species as the famous fossil skeleton known as Lucy. Take a moment to really picture that. More than 3.5 million years ago, at least 2 individuals walked side by side across wet volcanic ash, which then hardened and preserved their footsteps almost perfectly, like a message accidentally sent forward through unimaginable spans of time. And here's the detail that genuinely surprises people. Analysis of the footprints shows a clear heel-to-toe walking pattern, remarkably similar in mechanical structure to how modern humans walk today. Not a shuffling, ape-like gait. A genuine, striding, upright walk. By this point in the story, roughly 3.6 million years ago, upright walking wasn't some emerging experimental trait anymore. It was already a well-established, functioning way of life. What makes the Laetoli footprints even more remarkable is what they preserve beyond just the walking pattern itself. Researchers have identified what appears to be evidence of at least 2, and possibly 3, individuals walking together along the same path, at roughly the same time, based on how the footprint trails overlap and align. Some researchers have even suggested one set of prints may show a smaller individual stepping carefully inside the larger footprints left just ahead of them, though that particular interpretation remains debated. Either way, it's an oddly intimate glimpse into a single, ordinary moment, a short walk across damp ash, shared by individuals who had no idea they were leaving behind one of the most important pieces of evidence in the entire story of human evolution. So the fossil and footprint evidence gives us a rough timeline, but it still leaves the biggest question hanging. Why did this shift actually happen? What advantage was worth trading away the stability of 4-legged movement? Here's where multiple competing ideas come into play. And to be honest with you, scientists still debate which factors mattered most. One major idea focuses on energy efficiency. Researchers comparing the energy cost of chimpanzee-style knuckle walking to human-style upright walking found that, over long distances, walking upright on 2 legs can actually burn significantly less energy than moving on all 4s in a similar quadrupedal posture. That might not sound dramatic in the short term, but multiply that energy savings across constant daily foraging, over a lifetime, across countless generations, and even a modest efficiency advantage could meaningfully affect survival and reproduction over time. Researchers studying this question, including work by scientists Michael Sokol, David Raiklin, and Herman Poncer, measured oxygen consumption in chimpanzees moving both on two legs and on all fours, comparing the results to human walking. The findings suggested that human bipedal walking is considerably more energy efficient than quadrupedal knuckle walking, and even more efficient than the way chimpanzees themselves walk on two legs when they occasionally do so. That last detail matters, because it suggests our ancestors didn't just start walking upright the way a chimpanzee awkwardly does when standing briefly. Over time, the human body was reshaped specifically to make upright walking remarkably efficient, in a way that simply standing up on two legs, without deeper anatomical change, wouldn't achieve on its own. Another major idea is sometimes called the provisioning hypothesis, associated with the work of researcher Owen Lovejoy. This idea suggests that standing upright freed the hands in a very specific, important way. It allowed individuals to carry food. Think about what that actually enables. A hominin that can walk upright while carrying fruit, nuts, or other gathered food in its hands, back to a mate or offspring waiting elsewhere, has a meaningful advantage over one that can only eat what it finds on the spot, or awkwardly stuff into its mouth while moving on all fours. Under this idea, upright walking may have been deeply tied to changing social and reproductive behavior, not just simple movement efficiency. There's also a thermoregulatory idea worth mentioning here too, connected to something we've actually explored in another video on this channel, about why humans lost their body hair. Standing upright exposes less of the body's surface area to direct overhead sun compared to a horizontal, four-legged posture, potentially helping manage heat in hot, open environments. It's likely one contributing factor among several, rather than the single full explanation on its own. A few other hypotheses exist too, including ideas about upright posture improving displays of size or status, or assisting movement through shallow water in certain environments, though these remain far less broadly supported by the fossil evidence than the ideas we've already covered. It's also worth remembering that different hypotheses aren't necessarily competing against each other in a winner-takes-all way. Evolution rarely rewards a single trait for just one reason. A trait that saves energy while foraging, frees the hands for carrying food, and modestly helps with heat management could easily be favored by natural selection for all of those reasons simultaneously, reinforcing each other, generation after generation, rather than one advantage single-handedly outweighing all the rest. Most researchers today lean toward a combination of factors working together: energy efficiency, freed hands for carrying and tool use, and possibly thermoregulation, rather than one single dominant cause acting completely alone, especially since the transition happened gradually, across multiple species, over millions of years. Now here's a fun fact that tends to genuinely surprise people. Walking upright isn't actually as simple, biomechanically, as it might feel to us today. Balancing an entire body weight on two narrow points of contact with the ground requires an enormous amount of coordinated skeletal and muscular adaptation. The human spine developed a distinctive S-shaped curve instead of the more C-shaped curve seen in most four-legged animals, which helps center our body weight directly over our hips and feet. Our pelvis became shorter and bowl-shaped, anchoring crucial muscles that stabilize the body with every single step. Even our big toe shifted position over time, aligning with the other toes instead of angling outward the way it does in tree-climbing apes, creating a more effective, stable push-off point for walking and running. None of these changes happened instantly. Each one represents a small, gradual adjustment, refined and tested across an enormous span of evolutionary time. Here's another fun fact. Learning to walk upright as an individual, not as a species, but as a single human baby, remains a genuinely difficult, multi-month process, even today. Human infants typically don't achieve stable, independent walking until around 12 months of age or later, an unusually long developmental period compared to many other mammals, some of which can stand and move within hours of birth. Some researchers suggest this reflects just how biomechanically complex and finely tuned upright walking really is, requiring careful neurological and muscular development that simply can't be rushed. One more fact worth knowing. Bipedalism didn't just change how our ancestors moved. Many researchers argue it likely set the stage for numerous other major changes throughout human evolution, including eventually freeing the hands enough to support sophisticated tool-making, changes to breathing and vocalization that some researchers connect to the eventual development of complex language, and even shifts in childbirth and pelvis structure that continue to affect human anatomy today. So, after all of this, walking upright starts to look less like some strange evolutionary misstep, and much more like a foundational decision that quietly enabled almost everything that came afterward. It's strange to think that something as ordinary as putting one foot in front of the other, something most of us do without any conscious thought thousands of times a day, represents millions of years of gradual, careful, biomechanical trial and error, written directly into the shape of our spine, our hips, our feet, and even the timeline of how long it takes a baby to finally take that first wobbly step. So here's something worth thinking about. If a set of footprints pressed into volcanic ash 3.6 million years ago could still tell us this much about how our ancestors moved through the world, what other quiet, ordinary parts of how we live today might be hiding an equally deep and surprising history, just waiting for someone to notice the pattern?